Okay, here we have the thermocouple. So this is the thermo junction of the thermocouple. This is the thermocouple junction. So here, what we have to do is this thermocouple is made up of two different materials. Okay, so the junction of those two materials, that we call the thermocouple junction, and that will be the point which will be sensing the temperature. So if there is a difference, so there will be two junctions, one here and the other junction will be inside the transponder. So if there is temperature difference between these two junctions, so one junction will be inside the transponder and one junction will be outside. So if there is temperature difference across these two junctions, then an electromotive force or EMF will be created, and that will be measured by the transponder, and that converts the electrical energy into temperature. So whatever EMF produced proportional to that, there will be a conversion factor, and considering that, the uh, transducer will convert the reading into temperature, and it will display it uh, on the it will display it based on whatever units we have asked it for. It can display temperature in Kelvin, it can display temperature in degrees Celsius or Fahrenheit or Rankine. Whatever scale you choose, in that scale, it will display the temperature. So these two junctions, one we call it as hot junction and the other one we call it as cold junction. So the hot junction will be in contact with the hot fluid, and the cold junction will be in contact with the cooler surface or with the atmosphere. Okay, so here this thermocouple junction, this can be approximated as a sphere. So it is circular in shape. So we can assume that to be a sphere. If you are assuming that as a sphere, then we can apply lump system analysis. So we'll find out the Barrett number whenever we are solving problem. We'll find out the Barrett number, and if the Barrett number value is less than zero point 0.1, then we can go for lump system analysis. And since the size of the thermocouple junction is very small, generally we can directly apply lump system analysis in those cases. Okay, so when it comes to lump system analysis, we know that theta by theta I is equal to e to the power of minus tau by t if Barrett number is less than 0.1. So this is the condition or criteria for application of lump system analysis, where tau is the time and t is the thermal time constant. And we know that t tau minus ta divided by ti minus ta is equal to e to the power of minus tau by t. So here, what should happen is this term, that is e to the power of minus tau by t, should be very close to zero. So it should move towards zero as quickly as possible, because we need the fluid temperature and the temperature of the thermocouple junction. So the temperature of this junction, that will be T tau. So T tau minus Ta should be approximately zero, or it should vary at a faster pace, it should approach zero. So that is the condition, or that is the requirement for a thermocouple. So the response time is the time which the thermocouple takes, where the T tau will be T tau will approximately equal to Ta, maybe 99% equal to Ta, like that. So if T tau approaches Ta at a very faster pace, then we can say that the response time of a thermocouple is good. It's a very short, so the thermocouple is a good thermocouple. So here, uh, if I uh, if I want to reduce this to zero, then I'll write this as e to the power of the basic components, which is e to the power of minus h into a into tau divided by rho Cp into V. So this is the basic form of equation which we have. So if I want to reduce this term to zero, then this term should be maximum. So this term should increase. So if minus HA tau, or instead of minus, I'll just consider HA tau. HA tau divided by rho Cp into V. This value should increase. So if this entire value increases, then e to the power of, we have minus that value. So because of that, uh, this term e to the power of negative to a higher number will be very close to 0. So that is the requirement for a thermocouple. So if this entire value has to increase, then either we need to increase the ratio A by V. So A by V, there are several conditions which will lead to increase in this value. So we need to reduce the value of A by V, or A by V is nothing but 1 over LC. So LC should be increased to get A by V a negative value. So that is one condition. And then we can decrease the density and specific heat. So rho Cp, the second is reduce rho Cp. If you reduce the value of denominator here, then naturally the numerator, so the entire ratio increases. So that is another thing which you can do. Or the third one is increase H. If you increase H, then that is another case which is possible. So if you increase the heat transfer coefficient, then you can increase this entire term. So that will, the e to the power of minus a larger term will be equal, approximately equal to 0. So these are the things which can be done to increase the response time of a thermocouple. So now we have this equation, that is T tau minus Ta divided by Ti minus Ta, which is equal to e to the power of minus tau by T. And we had defined a term called time interval. So one time interval is nothing but when tau will be equal to T. So when the time is equal to thermal time constant, then if I substitute that here, we will get the ratio T tau minus Ta divided by Ti minus Ta is equal to e to the power of minus 1, and this is equal to 0.368. If you remember the derivation, so there we had used this term. So this is the one time interval. So generally, if we achieve one time interval, then this ratio will be 0.368, or T tau minus Ta will be equal to 0.368 times of Ti minus Ta. That is, now the temperature difference between the thermocouple junction and the fluid is 36.8 times of the initial temperature difference between the thermocouple and the fluid. Or in other terms, I can say that we have achieved 63.2% of the initial temperature difference has been achieved. So now we still have 36.8% to achieve, but we have already achieved 63.2%. So generally what we do is we will measure the temperature with the help of a thermocouple after it reaches at least 3 to 4 time interval. So that is the response time. So for a thermocouple, so if we are going for 3 to 4 time intervals, then in the first time intervals, we have already achieved 63.2%. In the second interval, we will achieve 62.3% of the remaining 36.8. So that is 63.2 plus 63.2 times of 0.368. And if we go to another time interval, then that will be plus whatever we get time here. that multiplied by 0.368. So we will be very close to 95, 96% at the end of the fourth time interval. So that is the response time. And this time required to reach 63.2% of the initial temperature difference, that we call it as the sensitivity of the thermocouple. It is the sensitivity of the thermocouple. So if the value of time required to reach 63.2%, that is one time interval, is smaller, then we say that the thermocouple is more sensitive than another thermocouple which has a larger value of time. The problem states that a thermocouple junction, which may be approximated as a sphere, is to be used for temperature measurement in a gas stream. To make it stream, the convection coefficient between the junction surface and the gas is 400 watt per meter square Kelvin, and the junction thermophysical properties are K equals 20 watt per meter Kelvin, Cp equals 400 joule per kg Kelvin, rho equals 8500 kg per meter cube. Determine the junction diameter needed for the thermocouple to have a time constant of 1 second. If the junction is at 25 degrees Celsius and is placed in a gas stream that is at 200 degrees Celsius, how long will it take for the junction to reach 199 degrees Celsius? So this is the problem. So here we have a thermocouple junction which may be approximated as a sphere. So here itself he says that it can be approximated as a sphere, and this is used to measure the temperature of a gas stream. Make it as STREAM. The convection coefficient between the junction surface and the gas is 400 watt per meter square Kelvin, and the thermophysical properties of the junction are, that is, thermal conductivity is 20 watt per meter Kelvin, and specific heat is 400 joule per kg Kelvin, and the density is 8500 kg per meter cube. Now we need to determine the diameter of the junction if it has a time constant of 1 second. So if the time constant, that is small t, is 1 second, then we need to find out the diameter of the junction. And then if the junction is at room temperature, that is 25 degrees Celsius, and is placed in the gas stream, which is at 200 degrees Celsius, how long the junction will take to reach a temperature of 199 degrees Celsius? Okay, let us list out the data here. We have a thermocouple junction, and that can be approximated as a sphere, and that is used to measure the temperature of a gas stream. So the convective heat transfer coefficient is given. So convective heat transfer coefficient between the gas stream and the thermocouple is 400 watt per meter square Kelvin. The junction thermophysical properties, that is, the thermal conductivity of the junction is 20 watt per meter Kelvin. The specific heat of the junction is 400 joule per kg Kelvin, and the density is 8,500 kg per meter cube. Now we need to determine the diameter of the thermocouple junction. The diameter needs to be calculated. If the time constant, that is small t, is 1 second, the time constant is 1 second, we need to find out the diameter. And if the initial temperature of the junction is 25 degrees Celsius and the fluid temperature is, surrounding fluid temperature is 200 degrees Celsius, then we need to find out the time required if theta is 199 degree Celsius. So we need to find out the diameter and we need to find out the time required. So I'll start with the solution here itself. Now first, let us find out the diameter. For the diameter, what they have given is, they have given the time constant value, and we know that T is given by H into A divided by rho Cp into V, or this can be T is rho Cp V divided by H into A, rho Cp V divided by H into A, or V by A can be written as Lc. I can write it as rho Cp into Lc divided by H. And for a sphere, we know that for sphere, we know that Lc will be equal to R divided by V. So from this, we will know the radius. Once you know the radius, you can find out the diameter. Okay, so now let us use this equation and find out the characteristic length. So from this equation, I can write Lc will be equal to T into H divided by rho into Cp. Now let us substitute the values. T is 1 second multiplied by H is 400 divided by density is 8,500 into Cp is 400. So these two will get cancelled. So Lc will be equal to 1 divided by 8,500. What is the characteristic length?
1.176 into 10 power minus 4.
1.176 into 10 to the power of minus 4 meters. So this is the characteristic length. And I know that Lc is equal to R divided by 3. So from this, I can calculate the radius, which implies that radius will be equal to 3 times of characteristic length Lc. So R will be equal to 3 into 1.176 into 10 to the power of minus 4, which is equal to
3.528 into 10 power
3.528 into 10 to
into
the
10
power
power
of minus 3 na?
minus 4.
It should be minus 4 meters. And I need the diameter. Diameter will be equal to twice the radius. So that is equal to 2 into 3.528 into 10 to the power of minus 4, which is equal to
7.056 into 10 power minus 1.
7.056 into 10 to the power of minus 4 meters. We will keep the diameter in either millimeter, centimeter, or meter. So here, since the value is smaller, so we can keep it in millimeter, and I can write the diameter as 0.7056 millimeter. So to have a time response or a time constant of 1 second for the given thermocouple junction and the condition of heat transfer coefficient, we need to have a diameter which is less than 1 millimeter. So the junction diameter should be very, very small. So that is 0.7056 millimeter is the junction diameter. So now we have calculated the junction diameter. Now we need to calculate the time required to reach 199 degrees Celsius. And for that, first let us calculate the Barrett number. So Barrett number is given by H into LC divided by K. Without LC, we cannot calculate Barrett number. Here, H is 400 into LC is 1.7176 into 10 to the power of minus 4 divided by K is 20. So Barrett number will be equal to
2.352 into 10 power minus 3.
2.353
2
okay 352
into 10
10 to the
power
power
minus 3.
minus 3, which is less than 0.1. So we can use lump system analysis here. So now we'll apply the equation for lump system analysis. That is, I'll directly write T tau minus TA divided by Ti minus Ta will be equal to e to the power of minus tau by T. Now I know T tau, I know Ta, Ti, and the small t. The only unknown will be tau. Let us substitute the values. T tau is 199 degree minus Ta is the fluid temperature, that is 200 degree, divided by initial temperature is 25 minus 200, which is equal to e to the power of minus tau divided by 1, because that is the time constant. Time constant is 1 second. So now calculate the time. Okay, here we have minus 1 divided by minus 175. Minus minus will get cancelled.
Sir, 5.1647.
So tau will be equal to 5.1647 seconds. Or approximately you can call it as 5 seconds. It takes 5 seconds to reach 199 degrees Celsius. So if you read the temperature before 5 seconds, then whatever you are reading is wrong for the given set of conditions. Should we go to next problem? Okay, we have one more problem here. The problem states that a 12 millimeter diameter MS sphere at 540 degrees Celsius is exposed to cooling air flow at 27 degrees Celsius, and the heat transfer coefficient is 114 watt per meter square Kelvin. Find first one, time required to cool the sphere from 540 degrees Celsius to 95 degrees Celsius. Second one, instantaneous heat transfer rate 2 minutes after the start of cooling. And third one, total heat transfer from the sphere during the first 2 minutes. Properties of MS are density 7850 kg per meter cube, specific heat 475 joule per kg Kelvin, and alpha is 0.045 meter square per hour. Here we have a 12 millimeter diameter sphere. The diameter is 12 millimeter. I can write the radius as 6 millimeter, which is equal to 0. You can write it as 6 into 10 to the power of minus 3 meter, or 0.006 meters. That is the radius. Then the sphere is at 540 degrees Celsius. So the initial temperature of the sphere is 540 degrees Celsius and is exposed to cooling air flow at 27 degrees Celsius. So the cooling air flow or the surrounding fluid temperature TA is 27 degrees Celsius. And the heat transfer coefficient between these two is H, which is 114 watt per meter square Kelvin. Now we need to find three things. First one, we need to find the time required for the sphere to reach from 540 degrees Celsius to 95 degrees Celsius. So from 540 degrees Celsius to 95 degrees Celsius, what is the time required? That is from initial temperature to some temperature theta, what is the time required? That we need to find out. Second one, we need to find out the instantaneous heat transfer rate, that is Q tau, needs to be calculated at tau equals 2 minutes. 2 minutes, which can be written as 120 seconds. Then third one, we need to calculate the total heat transfer rate, that is Q total, (2 minutes) or for first 120 seconds. These are the three things which you have to calculate now, and the properties are given. For mild steel, the density is given as 7,850 kg per meter cube. Specific heat is given as 475 joule per kg Kelvin, and alpha is given as 0.045 meter square per hour. So these are the data given in the problem. The first thing is to find out the Banach number and see whether lump system analysis can be used or not. So to calculate the Banach number, we know that Banach number is given by H into LC by K. First we need to calculate LC, and we know that it is a mild steel sphere. So for sphere, LC is given by R by 3. So the radius is 0.006 meter divided by 3, which will be equal to 0.002 meters. So this is the characteristic length. Now let us substitute that value in the Banach number and find out the Banach number. So Banach number is H. H is 114 multiplied by LC is 0.002 divided by K. Thermal conductivity is, are they given thermal conductivity here?
No.
Then how to find out the Banach number now? So here, instead of giving thermal conductivity, they have given alpha. If you remember the general three-dimensional conduction equation derivation is given by
K divided by rho Cp.
K divided by rho into Cp. So here they have given the value, we know the value of rho into Cp, and alpha is known. From this we need to calculate K, or in other terms I can write K will be equal to rho Cp into alpha, and alpha here they have given it in terms of meter square per hour. That should be converted into per second. So that should be substituted here. So let us try to calculate this. Rho is 7,850, Cp is 475, and alpha is 0.045 meter square per hour. How do you convert per hour to per second?
Divided by 60 into 60.
Yeah, you have to divide everything by 3,600. That is 60 into 60. Now calculate the value of K.
46.609.
46.609 watt per meter Kelvin. Now I'll substitute 46.609 here. So Banach number is 114 into 0.002 divided by 46.609. So we'll get the Banach number as
4.89 into 10 power minus 3.
4.89 into 10 to the power of minus 3, which is less than 0.1. So we can go with lump system analysis. Okay, now we need time, we need Q tau, and we need Q total. So first let us calculate tau. And for lump system analysis, we know that T tau minus Ta divided by Ti minus Ta will be equal to e to the power of minus tau by T. So let us calculate T. Radius is 0.003 squared multiplied by 108.91 minus 27. What is the instantaneous heat transfer rate?
1.056.
1.056 1.056 watts. Is that correct? Okay, this is the answer or second sub question. Now we need to find out the total heat transfer rate from the beginning of cooling till 1/20th second. Q total. So Q total can be calculated in two ways. One is calculating the instantaneous heat transfer rate from 0th second to 1/20th second and then adding them together. That is one case. So in the derivation, we had shown that it is like integrating from 0 to tau. So if you integrate Q tau, that is instantaneous heat transfer rate from 0 to tau, then you will get Q total. Or we have another equation which is mCp into T tau minus Ti. That is the changing mass of the object multiplied by specific heat of the object. There is the change in the internal energy of the object. T tau is the temperature at the 1/20th second minus Ti is the initial temperature of the object. So using this, we can find out the change in internal energy. So that will give us the total amount of heat removed, in this case heat removed from the object. If it is heating, then heat added to the object. So now let us calculate Q total. We already know the temperature at 1/20th second. So this is the temperature at 1/20th second. I can use that here directly. Instead of calculating it again, I can use the same temperature here. And the mass is given by volume into density into Cp into T tau minus Ti. Yes?
Sir, R is equal to 6 mml, sir.
Correct. That's why we are getting wrong answer here.
0.006.
This is 6 mm, 0.006. Please calculate the value. What is the instantaneous heat transfer rate?
4.22, sir.
4.22.
Okay, 4.22 watts. That is the instantaneous heat transfer rate. Now let us calculate Q total. And the volume for a sphere is given by 4/3 pi r cube into rho into Cp into T tau minus Ti. So Q total will be 4/3 into pi into R is 0.006 cubed into 7,850 into 475 multiplied by 108.91 minus 27. So that will give us Q total
276.33.
276.339.
339.
Now, what is the unit for total heat transfer?
Joules.
Yeah.
Watt per meter.
No, this is joule.
Watt per meter.
If you look at this equation, we have mass, that is kg, into Cp, that is joule per kg Kelvin, into change in temperature, that is Kelvin. Okay, the Kelvin will get cancelled. Kelvin will get cancelled. Kg will get cancelled. We will be left with joule. That is the unit of total heat transfer. Here I'm not talking about the rate at which heat is being transferred. Here I'm talking about the total amount of heat which has been removed. And sorry, here it should be Ti. Again, I have made a mistake here. I had taken Ta, but it should be Ti. So it is 108 minus 108.91 minus 540. So we should get a negative value because the sphere is losing heat here.
Minus 1,455.
Minus 1,454.
4.36.
0.36 joules. So this is the total amount of heat removed from the sphere. Okay, this heat is removed during the first 120 seconds of the cooling process. It is not the total entire amount of heat removed, but this is the amount of heat removed during the first 120 seconds. And we have one more heat transfer. I'll write it here. That is Q max. So this is the maximum amount of heat which can be removed from the object, and this will be given by mCp into Ti minus Ta. Since I'm talking about heat removal, I have written Ti minus Ta. If it is heat addition, that becomes Ta minus Ti. Okay, this is difference of these two. So mCp into the temperature of the solid changes from initial to fluid temperature, or the heat transfer occurs till these two temperatures are equal. So this is the maximum possible heat transfer that can occur in the process. So this is, make a note of this. I think we have not talked about this. Again, M, in place of M, I'll write it as volume into density, and that is 4 by 3 pi r cube into rho. I'll write the same here, 4 by 3 pi into 0.006 cube into 7850 multiplied by Cp is 475 into temperature difference is initially it is 540, and that can reduce up to the fluid temperature, which is 27 degrees Celsius. So till 27 degrees Celsius, the temperature of the sphere can
1,730.
1730
0.70.
0.70. Again, the unit is joules, and if you take it as Ta minus Ti, then you will get it as negative, which means that is the maximum amount of heat that can be removed from the object. So this is not the rate at which we are removing. This is the total amount of heat which we are removing. Okay, here we have a 40 by 40 centimeter copper slab, which is 5 millimeter thick, of a uniform temperature of 250 degrees Celsius. Suddenly has its surface temperature lower to 30 degrees Celsius. Find the time of which the slab temperature becomes 90 degrees Celsius. This is 90 degrees Celsius. Take the following properties for copper. That is, rho is 9000 kg per meter cube. Then Cp is 0.38 kilojoule per kg Kelvin, and K is 370 watt per meter Kelvin, and H is 90 watt per meter square Kelvin. Note down the problem. So till now, whatever we solved on spheres. Now let us solve problems on different geometries. We have cube, we have slab, and we have cylinder. So we'll try to solve problems on few of those things. Okay, we have a slab, a copper slab, and that has an area of 40 by 40 centimeter. So the area A will be equal to 0.4 by 0.4, which is equal to 0.16 meters square. That is the area of the slab, and it has a thickness of the slab is, I'll call it as 2L. If you remember the characteristic length definition, we had called this as 2L. So 2L is 5 millimeter. So that is the thickness of the slab. And the slab was at a uniform temperature of 250 degrees Celsius. So its initial temperature is uniform, and that was 250 degrees Celsius. Currently, it has its surface temperature lower to 30 degrees Celsius. It means to say that it is now surrounded by a fluid which is at 30 degrees Celsius, because the fluid will be in contact with the surface. So the fluid temperature is 30 degrees Celsius. Find the time for which the slab temperature becomes 90 degrees Celsius. Now we need to find out the time when, or if the temperature of the slab becomes 90 degrees Celsius. Okay. Take the following properties of copper. So the density is given as 9,000 kg per meter cube. Then the specific heat is given as 0.38 kilojoules per kg Kelvin. I'll write it in joules per kg Kelvin. That is 380 joules per kg Kelvin. Then thermal conductivity is 370 watt per meter Kelvin, and the heat transfer coefficient H is given as 90 watt per meter squared Kelvin. So with this, we need to find out the time required for the slab to reach 90 degrees Celsius. So whenever we are solving any problems in transient conduction, first and foremost is to find out the Barrett number. So the Barrett number is given by H into LC divided by K. We know the value of H and we know the value of K. Now we need to calculate LC. And if you remember the definitions for characteristic length, for a slab, the characteristic length is half of thickness. So here it is half of 5 millimeter, or 5 into 10 to the power of 5 minus 3 meters. So it is 2.5 into 10 to the power of minus 3 meters. That is the characteristic length. Now let us calculate the Barrett number. The Barrett number is given by H into LC by K. H is 90 into 2.5 into 10 to the power of minus 3 divided by K is 370. So what is the value of Barrett number?
6.08 into 10 power minus 1.
6.08 into 10 to the power of minus 4, which is less than 0.1. Okay, we need to write the statement now. Since Barrett number is less than 0.1, we can go with lump system analysis. So now I'll write the equation for lump system analysis. We know that T tau minus Ta divided by Ti minus Ta will be equal to e to the power of minus tau by T. Now let us calculate the thermal time constant T. T is given by rho Cp Lc divided by H. Density is 9,000 multiplied by Cp is 380 multiplied by Lc is 2.5 into 10 to the power of minus 3. Everything divided by H. H is 90. What is the thermal time constant?
95.
95 seconds. That is the thermal time constant. Now let us use this and find out the time required to reach 90 degrees Celsius. So T tau is 90 minus Ta is 30 divided by initial temperature is 350 No, 250. 250 minus 30 will be equal to e to the power of minus tau divided by 95. Calculate the value of tau.
23.43.
So tau will be equal to 123.43 seconds. So this is the time required by the surface to reach 90 degrees Celsius. The only difference here is characteristic length, except that everything remains same. If you calculate the characteristic length properly, then the rest of the procedure remains same. It can be, you can call it as a cylinder. So the diameter of that is 60 millimeter, and it was initially at a temperature of 800 degrees Celsius, and that is suddenly dropped into an oil bath. So it is surrounded by oil, and the oil temperature is 50 degrees Celsius, and the heat transfer coefficient between the oil and the surface is 400 watt per meter square Kelvin. The properties of the ion are given, that is K and alpha are given. Cp is not given in this case. So you need to use alpha to calculate Cp, and the density is also not mentioned in the problem. For that you have to go to the data handbook, or you can use the product of rho into Cp in the problems directly. And now we need to calculate the center line temperature. So the center line, so here you have the center line. You need to find out the center line temperature 10 minutes after the immersion in the fluid, and then you need to find out how long will it take for this center line to reach 100 degrees Celsius, and also you need to find out the total amount of energy removed, that is Q total, during 10 minutes time, that is from the initiation of cooling till 10 minutes, what is the amount of energy removed. Okay, now let us list out data. So I have the diameter is 60 millimeter. I can write radius as 30 millimeter or 0.03 meters. 30 millimeter is nothing but 3 centimeter or 0.03 meter. And it was initially at a temperature of 800 degrees Celsius, and that is suddenly immersed in an oil bath. So the temperature of the oil bath or the surrounding fluid is 50 degrees Celsius, and the heat transfer coefficient between these two is 400 watt per meter square Kelvin. The properties of iron are given, that is alpha, thermal expansion coefficient is 2 into 10 to the power of minus 5 meter square per second, and thermal conductivity is 60 watt per meter degree Celsius. So these are the data given. So we have three things to calculate here. A, we need to find out the center line temperature. So center line temperature 10 minutes after the immersion, that is when tau equals 10 minutes or 600 seconds. At that time we need to find out the center line temperature. Then B, we need to find out how long will it take, that is tau equals question mark is 100 degrees Celsius. Okay, then we have another part, another sub question, which is we need to find out the energy removed from the rod during 10 minutes. It is Q total equals question mark for first 10 minutes or 600 seconds. Okay, we have three parts. So here I'm writing this as central line temperature because I don't know whether I can use lump system analysis or not. So if I'm able to use lump system analysis, then the central line temperature and temperature anywhere within the rod will be same. That is the assumption which we have made in the lump system analysis. The assumption is the temperature within the body is uniform. So whether it is central line or at any other radius or at the surface, the temperature should remain same. So first, let us calculate the Barrett number. Once we calculate the Barrett number, then we can say whether we can apply the lump system analysis or not. If it is applicable, then the temperature of the center and the surface will be same. So Barrett number is given by H into LC divided by K, where LC is the characteristic length. Now we are dealing with a cylinder. So for cylinder,
V by A.
characteristic length is for a long cylinder, it is radius by 2, half of the radius. Okay, we have done the derivation here. Volume will be equal to cross-sectional area multiplied by the length divided by the surface area will be equal to circumference, that is 2 pi r into length. So when you simplify that, we will get characteristic length as radius by 2. So here the radius is 0.03 divided by 2, which is 0.015 meter. That is the characteristic length. Now let us calculate Barrett number. Barrett number will be equal to H is 400 into 0.015 divided by thermal conductivity is 60. So what is the value of Barrett number?
0.1.
0.1. So here Barrett number is exactly 0.1. So we can solve this problem. So by the definition, this is not less than 0.1, but it is equal to 0.1. So the thing is, we can apply lump system analysis, but the accuracy of the result cannot be, will not be less than 5%. So sorry, 95%, or the error will be more than 5%. As of now, since we don't know any other method, let us apply lump system analysis and try to solve these three problems. So in the next class, I'll talk about the other methods of solving the transient problems, and then we'll take up the same problem and try to solve using the graphical method. Then we will see the difference. If there is for point 1, can we use lump system or not, we will get to know in the next class. So now let us use lump system analysis. Okay, for a lump system analysis, I'll start with A. We need to find out, since I'm considering it as a lump system analysis, so the temperature anywhere on the rod will be uniform, and I can consider that as T tau. Now I need to find out T tau when tau is 600 seconds. T tau minus Ta divided by Ti minus Ta will be equal to e to the power of minus tau by T. So let us calculate T. T is given by rho Cp into Lc divided by H. Now we don't have the value of rho as well as Cp, but we know alpha. So alpha is given by K divided by rho Cp. So from this I can write rho into Cp will be equal to K divided by alpha. I will use the product directly instead of finding out rho and Cp separately. So K is 60 and alpha is 2 into 10 to the power of minus 5 meters squared per second. So what is the product of rho into Cp?
3 into 10 power 6.
3 into 10 to the power of 6. And what will be the unit? So the density has kg per meter cube and Cp has joule per kg Kelvin. So kg will get cancelled. We'll be left with joule per meter cube Kelvin. So joule per meter cube Kelvin. Okay. So we'll use that. So now T will be equal to rho Cp is 3 into 10 to the power of 6 multiplied by Lc. Lc is 0.015 divided by H. Heat transfer coefficient here it is 400 watt per meter square Kelvin. What is the value of T?
112.5.
412.5 seconds.
Sir, 112.
112.5 seconds. So now let us calculate the temperature T tau. So I'll substitute the values T tau minus TA. TA is 50 degrees Celsius divided by initial temperature is 800 minus 50 will be equal to e to the power of minus tau is 600 divided by 112.5. So T tau will be equal to
53.62.
53.6 degrees Celsius. So the temperature is very close to 50. By 10 minutes, most of the heat has been removed from the iron rod. So now this is the answer for sub-question A. Now let us look what we have to calculate in sub-question B. Sub-question B, we need to calculate the time required when the center line temperature is 100 degrees Celsius. So for B, we need to calculate tau if T tau is 100 degrees Celsius. I'll use the same equation here. So T tau is 100 minus 50 divided by 800 minus 50 will be equal to e to the power of minus tau. I don't know tau divided by 112.5. Now calculate tau.
304.65.
So tau will be equal to 304.65 seconds. So to reach 100 degrees Celsius, it requires 304.65 seconds or approximately 5 minutes. Now we have the last part. The last part is to find out the total heat removed during the first 10 minutes. Again, we know the equation, so this is answer for sub-question B. So now we have C. C is Q total. MCP into T tau minus Ti. So now I need to calculate T tau. T tau, here we have already calculated T tau for 10 minutes or 600 seconds. So I'll use the same thing here. And mass is given by volume into density into Cp into T tau minus Ti. Now we are dealing with cylinder. For a cylinder, the volume is cross-sectional area multiplied by the length. Are they given the length here? In the problem, they have not mentioned the length. They have not given any data regarding to the length. So I'll consider the total amount of heat removed per unit length. So the volume is pi d square or pi r square by 4 multiplied by length multiplied by rho Cp multiplied by T tau minus Ti. I'll calculate, I don't know the length, so I'll calculate Q total per length, per unit length. Now I'll substitute the values. 5 by 4 into radius is, the diameter is 60, the radius is 30 millimeter or 0.03 meter square multiplied by, I know the value of rho Cp, the product of rho Cp we have calculated here, that is 3 into 10 to the power of 6 joule per meter cube Kelvin. So rho Cp is 3 into 10 to the power of 6 multiplied by T tau. So it is 53.6 degrees Celsius minus 800. The initial temperature is 800 degrees Celsius. Now calculate this. Q total
minus 1.58 into 10 power 6.
minus 1.58 into 10 to the power of 6, and the unit will be
Joule.
is joules per meter because that is per unit length. Or I can write it as minus 1.58 megajoules per meter. So for every 1 meter, 1.58 megajoules of energy will be removed from the rod.